Hello again. In this video, I'm going to go over section 2.1, part 2, which is about instantaneous velocity at a single point in time. Okay, so let's look at example 2, where we're going to estimate the instantaneous velocity of the rock in example 1 when t is equal to 1. Now you may remember the position function from example 1 was given by this equation. So this describes the position of the object at any given time t. And if we were to graph this function, it looks like this black curve right here. It's just a parabola that opens downward. Okay, so what we're going to do to estimate the instantaneous velocity of this rock when t is equal to 1 is we're actually going to find the average velocity between t is equal to 1 and some time a little bit larger than that. Okay, so let's find the average velocity between t is equal to 1 and let's say t is equal to 2. Now to find that average velocity, we need to find its position at time 2 and then subtract off its position at time 1, and then divide by the time period between 2 and 1, which is 2 minus 1, 1 second. Okay, so s of 2, we would just plug a 2 into this function here. And when you plug a 2 into that function, you get 128 out, which happens to be this point on this the graph of this position function. And when you plug a 1 in, you get 80 out, which is this point on the position function. Okay, and so the object has traveled 128 minus 80 feet, which is 48 feet, over a period of 1 second. And so it's traveling at 48 feet per second on average between those two time periods, or those two times. Okay, and you may remember from the last video that the line that goes through these 2 points is called a secant line, and the slope of that line is the same as the average velocity between these two time periods, namely 48 feet per second. And so that's our initial estimate for the instantaneous velocity when t is equal to 1. Okay, and what we're going to do is we're going to improve on that estimate by shrinking the time between t equals 1 and this larger time. Okay, so this time let's go between t equals 1 and 1.5 instead of 2. Okay, so we're shrinking the time period. Okay, so if you find the average velocity between these two times, at 1.5 seconds, the object is at 108 foot mark, minus its position at 1 second, which is still 80, so it's traveled at 28 feet, but over the course of 0.5 seconds. And so that turns out to be an average velocity of 56 feet per second between these two time periods. And this is a better estimate for the instantaneous velocity when t is equal to 1. And if you wanted to, you could come down here and find the secant line that goes through those 2 points, which would look like this green line here. And of course, the slope of that line would be the same as the average velocity between these two points in time, 1 and 1.5. Okay, and so this is the idea. If I want to get a better estimate for the instantaneous velocity when t is equal to 1, I just need to shrink the time period between t equals 1 and this larger time. Okay, so you may want to shrink it a little further and go between 1 and 1.1. And then you find the average velocity between those two times, and it turns out to be 62.4 feet per second. And that's a better estimate for the instantaneous velocity when t is equal to 1. And if you wanted to, you could find the slope of the secant line between those 2 points down here, and the slope of that line would be the average velocity between those 2 moments in time. Okay. So it should be at 1.1 if I can get it to there. Okay, between these two time periods. Okay, if you find the average velocity between these two time periods, it turns out to be 62.4 feet per second, which is the slope of the secant line between those 2 points. Okay, so if you just continue to do this, right, you go between these two time periods, you get this average velocity, which is a better approximation for the instantaneous velocity when t is 1. Every time you do this, and you find the average velocity between these two times, you're getting an estimate for the instantaneous velocity when t is equal to 1. So the question comes up, all of these are approximations, right? They're estimates. How do we find the exact instantaneous velocity when t is equal to 1? Okay, and so the answer is, what we're going to do is we're going to find the limit of these average velocities as this t value on this right-hand side approaches 1. So whatever the limit of the average velocities as t approaches 1, whatever that limit is, that's the instantaneous velocity when t equals 1. And I think you can see that these average velocities are getting closer to 64. It's 48, 56, 62.4, 63.8, 63.98, 63.998, right? You can see that they're approaching 64. And so that's the exact instantaneous velocity when t is equal to 1. It's the limit of these average velocities as t is approaching 1. So that's no longer an estimate. This is the exact answer for the instantaneous velocity when t is 1. Now that leads us to this idea of a tangent line. So when we're finding the average velocity between two moments in time, or 2 points in time, the average velocity between 2 points in time is equal to the slope of the secant line that goes through those 2 points on this position function. And you can see that as t approaches 1, that this green secant line is approaching this red line, which, by the way, has a slope of 64, which is the instantaneous velocity right when t is equal to 1. So this secant line, as t is approaching 1, this secant line is getting closer to this tangent line. In fact, the slopes of these secant lines are also approaching the slope of this tangent line, which happens to be 64. So a couple of things to take note of here. A secant line goes through 2 points on the position function, and the slope of a secant line represents the average velocity between those 2 points. Whereas a tangent line only goes through 1 point on the graph of the position function, and the slope of that tangent line represents the instantaneous velocity, or is equal to the instantaneous velocity, right at that single point in time, namely here when t is equal to 1. And I think you can see that the limit of these secant lines as t is getting closer to 1 is actually equal to the slope of the tangent line when t equals 1. Okay, in this case it's 64. Okay, so that's a couple of things you need to keep in mind. Secant lines begin to approach this unique line called the tangent line. So this green line is beginning to approach this red line, right? The secant lines get closer and closer to the tangent line. And the slopes of the secant lines as t approaches 1 get closer to the slope of the tangent line itself. when t is equal to 1. Okay, so just kind of to recap this, it's important that you sort of digest some of this. The slope of the secant line represents average velocity between the 2 points that the secant line goes through, and the slope of the tangent line represents the instantaneous velocity at this single point that the tangent line goes through on the position function. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.